Assalamualaikum warahmatullahi taala wabarakatuh. So in this video I am going to explain to you in detail how to draw the free body diagram and also draw the reaction forces of a mass spring damper system. Okay, so let's start with a simple mass spring damper system as shown in this figure. Okay, where you have a mass denoted by this M, you have a spring with a spring constant K, and a damper with a damping stiffness or damping coefficient of B. Okay, so this F of T is input force, so it means you are pulling this mass downwards. Okay, and this Y of T is the displacement, okay, of the system. Okay, so when you apply force downwards, the whole system will move downward. Okay, so the displacement denoted by Y of T. So now the question asks you to write to derive the differential equation that represent this system. Okay, so like I teach you in class, the first step that you wanted to do is draw the free body diagram. Okay, so step number 1 is draw free body diagram of the system. Okay, so in this case we have a mass. Okay, M. Or rather, let me just draw a little bit downward. Okay, so this is M. Right, now what information given to us is direction of force, which is downward. So we have here F of T, and also direction of motion, okay, or downward, which is Y of T. Okay, same direction as the direction of force. Now we wanted to draw reaction forces. Okay, so this one is actually from Newton's third law, or Newton's a combination of Newton's second law and third law actually. Okay, so Newton's second law says that when the body, okay, for example like this system, in a static condition, okay, means it's not moving. So when we apply a force, okay, that tries to move this mass, okay, there will be a resistance due to the inertia inside the body, okay, due to the weight of this mass, right? So there will be a tendency for this mass to keep its current condition, which is not moving. Similarly, if the system is currently moving and you apply a force to stop it, according to Newton's law, the system will not stop immediately. So instead, there will be a certain time, okay, time difference between when you apply force to stop it and when the system will eventually stop, okay, because the system will try to keep its current condition, which is the moving condition. So in this case, we have a system which is not moving, okay, and we apply force to move it. So the system, okay, due to the mass and due to the stiffness of the spring and the damper, will try to keep its non-moving condition. Okay, so according to Newton's third law, then, okay, there will be a reaction forces due to spring damper, due to the stiffness of the spring and the stiffness of the damper and the weight, okay, of this block. And the reaction forces will be opposite to the direction of motion. Okay, so you can read Newton's third law if you wanted a detailed explanation on that. Right, so in this case we have a spring and a damper and the mass itself. So we know that there will be a reaction forces due to the spring, the damper and the mass, and the direction of reaction forces is opposite to direction of motion, because the system will prevent, okay, the motion. So if we draw in this graph, let me just draw with a different color. Okay, so reaction forces, the reaction forces will be upward, direction upward, because this is the opposite to direction of motion. Okay, so here we will have K, Y, T, and b y dot t. And another one due to the weight of the mass itself, so it will be m y double dot t. Okay, so then step number 2 will be to write summation of force. Okay, force equals to 0. Right, so we can take, let's say, downward as positive sign because this is the direction of motion. So if you do that, and then we will have ft positive direction, and then m the reaction forces will be negative, so we will have m y double dot t minus b y dot t and minus ky of t equals to 0. Right, so now we can rearrange so that we have the reaction forces on one side and the input force on the other side. So we'll have f of t equals to m y double dot t plus b y dot t plus ky of t. And so this is the direction of the differential equation that represents this system, or we also call as equation of motion. Okay, equation of motion. Right, now let's have a look if we have a horizontal system like this. Okay, so again you have a mass, and then you have a spring and damper. This is applied force, so you can imagine that you are pulling this mass to the right, okay, so that you have a displacement, okay, in the same direction as the applied force. So the question asks you to determine the differential equation for this system. Okay, right, so first step is to draw the free body diagram. Okay, so step 1, draw free body diagram. This free body diagram is important, okay, because it tells you how many reaction forces you will have and what's the direction of the reaction forces. Okay, so if we draw that, and we have m, what information is given? We have the output, okay, which is displacement, and we have the input, which is force. Okay, so now we need to draw the reaction forces. So again, initially this system is a non-moving state. So when we apply force to move the system, okay, the weight of the mass and the stiffness of the spring and the damper will try to prevent motion. Okay, so that's why we will have reaction forces in the opposite direction of motion. Okay, so we will have here k x of t, we will have here b x dot of t, and we'll have m x double dot of t. Right, so then the next step is to write the equation of motion. So step number 2, you write the summation of force equals to 0. So in this case we can take positive to be in the right direction, which is direction of input force. So we will have f of t, then all the reaction forces will be negative, mx double dot t minus bx dot t minus kx of t equals to 0. Okay, so then you can rearrange, so you will have f of t equals to mx double dot t plus bx dot t plus kx of t. Right, so this is your equation of motion, or differential equation. Now let's have a look what happens if we have a more complex system, okay, where here this time you have a single mass, okay, m, and then you have two set of spring and damper. Okay, so you have the first spring and damper over here, k1 b1, and another set of spring and damper over here, k2 and b2. Okay, so you have applied force f of t over here, and then the displacement of the mass, okay, due to the applied force is given by this x of t, right? So it will be the same like before. To solve or to determine or to derive the differential equation for this system, you draw the free body diagram. Okay, so step 1, draw free body diagram. Okay, so what do we have? And we have mass. What else? We have direction of displacement, which is x of t, and we have input force, which is f of t. Okay, now we wanted to draw the reaction forces. Okay, so the easier one will be the one due to the mass, will be mx double dot of t. Okay, and we will have a reaction forces due to k1. So now you can imagine, okay, you are pulling this, okay, this mass to the right. So for this spring, okay, it will be elongated, okay, it will be expanded to the right. Okay, so this spring and damper will be pulled to the right as well. So there will be a reaction forces, okay, to prevent motion. So the reaction forces will be in the opposite direction of motion. So you will have over here k1x of t and b1x dot of t. Okay, similarly for this set of spring and damper, it will be compressed, right? So compressed to this direction. Okay, so this spring and damper will try to prevent that compression. Okay, so it will apply reaction force to this direction. Okay, that's why we have a reaction force in the opposite direction as well. Okay, for this side, represented by k2x of t and b2x dot of t. So the next step is to write the equation of motion. Oops. And write equation of motion, which is basically summation of force equals to 0, and then we can take positive direction to be to the right, which is direction of input force. Okay, so if we do that, we will have f of t positive, okay, and then the rest of the reaction forces will be negative. So let's start with the highest order differentiation, which is mx double dot of t. So we will have minus b1x dot t minus b2, and then minus k1 minus k2 equals to 0. Okay, and we can, I think, rearrange so that we have f of t equals to, then everything will become positive, right? It's t plus b1x dot t plus okay, now we have to say equation with similar terms, okay, which is this b1 and b2 and also k1 and k2. So we can simplify further the equation. So you will have f of t equals to mx double dot t plus b1. So let's put it in the bracket, b1 plus b2 x dot of t plus k1 plus k2 x of t, right? So this is your equation of motion or differential equation that represent this system. Now let's have a look at another type of system. What about if you have something like this? Okay, So in this case, you have two mass, M1 and M2, and then in between M1 and M2, they are connected, okay, using this spring and damper system. Okay, and a force F of t is applied to M1. Okay, so M1 will have a displacement, okay, output displacement of x1t, and M2 will have output displacement of x2 of t. And then again, the equation asks you to determine the differential equation that represent this system. Okay, so as usual, the first step is to draw the free body diagram. Okay, and this time we have two masses, okay, to M1 and M2, so you need to draw the free body diagram separately. Okay, so let's start with M1 first. We have M1, what is given? We have the displacement x1 of t, and we have the input force, which is F of t. Okay, so the easiest part for the reaction forces, so again, initially this system is non-moving. Okay, so when we try to push this system by applying this force, okay, so we're trying to move the system. Okay, so the weight of the mass as well as the stiffness of the spring and the damper will prevent motion. Okay, so there will be a reaction forces. Okay, so let me just draw the spring and the damper over here. Okay, so the spring and the damper, okay, here, okay, we are moving to the right, so this spring will exert reaction force in this direction and opposite to direction of motion, because it will try to stop motion. Okay, it wanted to keep its initial position, which is non-moving. Similarly, there will be reaction forces exerted over here due to this damper, okay, that will prevent motion, and another one, reaction forces due to the mass itself, okay, that will try to prevent motion. Okay, so here we will have M1 x1 double dot. Okay, then over here, so this spring try to prevent this motion, so we have k x1 of t, and this damper try to prevent this motion, so we have x1 dot t. Okay, however, you have to remember that this end of the spring and damper is connected to another mass, which is M2. Okay, so when we push, okay, this mass to the right, okay, this end, okay, this end of the spring and damper is also pushing, okay, M2, so the M2 will move, okay, so the M2 will move to the right. So therefore, okay, there will be a force in this direction, okay, exerted to M2 by the spring, and also another force exerted over here by the damper, okay, due to to move M2 to the right. Okay, so this force will be k x2 of t, because this force will produce motion of M2, which is denoted by x2 of t. Okay, similarly, the force over here will be b x2 dot of t. Okay, now let's have a look at M2. Okay, for M2, what is given to us is only output force, output displacement. Okay, and there is no input force, right? But however, this other side of the mass is connected to spring and damper, right? So when this mass move to the right, okay, in this direction, it will at the same time pull, okay, this spring and damper to this side. So this spring and damper will exert reaction force, okay, to stop this pulling to the right. So with respect to M2, okay, now we are looking at M2. Okay, so from the point of view of M2, this spring will exert a reaction force, okay, to prevent the motion to the right. Similarly, this damper will exert a reaction force, okay, opposite to direction of motion to prevent the motion to the right. And again, the mass itself will exert reaction forces to prevent motion to the right. So for the mass, it will be M2 X2 double dot. For this reaction force, it will be K X2, and for this one, it will be B2 X. Sorry, no K2. So it's just K, and this one just B X2 of T. But at the same time, this side of the spring is connected to M1. Okay, so this side of the spring, okay, is pulling M1 to the right, and this side of the damper is pulling M1 also to the right. So for this particular force, okay, it will be Kx1 of T, okay, because it will result to a motion of M1. Similarly, this one will be B x1 dot of T, okay, because the result of this force will be the movement of M1. Okay, so now we wanted to write the equation of motion. So we will have two equation of motion because we have two mass. Okay, so for M1, let me just write here. For M1, if we do summation of force equals to 0, and let's take positive as the right direction as positive. So we will have F of T minus M1 x1 double dot, and then we will have positive B x2 dot, and then minus B x1 dot. Okay, and minus positive K x2 T minus K x1. Okay, so this one equals to 0, right? So we can also rewrite. Okay, so we take all the reaction forces, okay, take it to the other side. So we will have equals to, then M1 x1 double dot. Okay, so this positive, this one positive will become negative. So we have minus B x2 dot. Let me just make it a little bit larger. And we have plus B x1 dot T, and then minus K x2 of T, and plus K x1. Okay, now we can put the one with the similar terms together, which is F of T equals to M1 x1 double dot, and we will have, if we put positive, we will have and let's put the B outside. Okay, so we will have this one dot x1 dot of T minus x2 dot of T, okay, which is from this part. Okay, similarly, if we put plus, and then we take the spring constant outside, K, we will have x1 of T minus x2 of T. Okay, Okay, so this is what I explained in our class last time, yesterday, that for M1, for example, okay, you can also draw M1. You can also draw the reaction forces, okay, as M1 x1 double dot t, and the direction is opposite direction of motion. You can also do B x1 dot minus x2 dot, and for the spring you can write K x1 minus x2. Okay, it is actually from this equation. Okay, so I hope you understand. I'm afraid the explanation during class yesterday was not quite clear. Okay, so let's have a look at the second mass. So for M2, if we do the summation of force equals to 0, okay, and since we don't have but we have this x, so let's just take positive in the right direction as well. Okay, so we will have this M2 as negative because it is to the left, so we will have minus M2 x2 double dot t, and we will have positive B x1 dot t, and then minus B x2 dot of t plus K x1 of t and minus K x2 of t equals to 0. Okay, however, the common practice is to write the equation of motion, okay, or the differential equation, so that this M will be okay in the positive terms. Okay, so that means the whole equation we have to multiply with minus 1. Okay, so that we will get this M as positive. So we will have M2 x2 double dot t. So this one become negative. Positive. This one negative. Positive. Okay. Now we have similar terms, so we can group them together so that we can have the equation of motion as M2 x2 double dot t plus, if we take the B outside, here we will have x2 minus x1, okay, which is from here. Okay, so we will have x2 dot t minus x1 dot t plus K. We will have again x2 minus x1, x2 of t minus x1 of t. Okay, so again, this is what I explained yesterday. Okay, when I say for M2, okay, direction of motion is this way for M2. Okay, so you can draw the reaction forces M2 x2 double dot, and the reaction forces for the spring over here, it will be K x2 minus x1. Okay, so this is what I explained yesterday. So it's actually from this equation. So I hope with this, you can understand better how do we come up with the notation or for the reaction forces. Okay, if you have a system like this. Now, what happens if you have a system like this, which is more complicated? Now you have two masses, okay, M1 and M2, and you have M1 connected to this non-moving wall through this K1 and K2 spring damper set, and also connected to M2 through this K2 B2 spring damper set, while M2 connected, okay, to M1 through this spring set, and also connected to this non-moving wall through this K3 B3 spring damper set. Okay, the output for M1 is denoted by X1, output for M2 denoted by X2, and here you have input force, okay, applied. Right, so you can solve this. Why don't you go ahead and try to solve this on your own, and then if you have tried, you can send the answer. If you want me to check your answer, you can send your answer to me through WhatsApp, or you can post it on our Google Classroom so that I can have a look, okay, whether you done right, okay, with the free body diagram and also the equation. But what you can do is you combine, okay, you combine this, how to say, the method that we applied to solve this system, okay, and also the method applied to solve this system, okay, because this one is the combination of the other two. Okay, right, so okay, I'm going to stop the video here, and we'll see you in the other video to explain okay, about other examples. Okay, thank you.